Good morning, everyone. I'm Yunfei Wang from SCAC. Today, I'm going to present how to use physics-based simulation to quantitatively address a fault displacement hazard and how to validate this methodology against the dataset from the 1992 London earthquake. From previous presentation in this session, we have already known the groundbreaking can directly cause significant seismic hazard. Then our question is if and how we can avoid or reduce this hazard. If we have some prior knowledge of probability about the location of active faults or when or how large of loss the rupture was, it definitely helps to decide where to construct. One such practical example is Alquist per Aulo Fault Zone Act in California. The intent of AP Act is to restrict the building of structures for human occupancy across active faults. So the key point is avoidance. However, a full avoidance of active faults is not very realistic. For example, as for the distributed infrastructures, gas line or water line, there are a potential multiple paths across a fault zone. It might be possible to avoid part of them, but it's extremely hard to avoid all of them. Another reason is that we are not able to find all the active faults because our observation period is too short. Some faults are buried and keep silent in the past few hundred years, but might be reactivated nowadays. Finally, for some special structures, they have been optimized in the locations already, and may not be able to avoid faults. For example, dam and nuclear waste repository. Therefore, we need a method to evaluate how dangerous of each known fault. USERF and our skill model may show occurrence probability. Besides, we also need evaluation of the amplitude prediction of the fault displacement hazard. Fault displacement demands used in engineering, design, or defined using probabilistic fault displacement hazard analysis, PFDHA or PUFDA. And PAFDA is also based on the empirical fault displacement dataset. Compared to empirical ground motion models like NGFS2, PAFDA models are sparse and poorly constrained partly due to the scarcity of detailed fault displacement observations. That is because only relatively larger screencasts of rupture and the very long recurrence time between the two co-located earthquakes. Number three, it is technically difficult to collect the very detailed perishable fault displacements. Therefore, this issue may hinder the PUFD model development. In this study, our goals are quantifying fault displacement through physics-based simulation and supplementing the empirical dataset with simulated fault displacement dataset. We use dynamic rupture model because the dynamic rupture model can impose stress, friction, fault geometry to gain a physically plausible simulated fault displacement profile. And additionally, with proper rheology model, the method can produce both on-fault and off-fault distributed inelastic deformation. For viable extrapolation of this methodology, simulation must first be validated against the data. To validate simulated fault displacement from dynamic rupture models, we choose the 1992 Landers earthquake for a validation exercise. In the field observation, the fault offset is like the left pattern, an abrupt change of deformation across a fault. That is to say, the fault offset seems along a line, but actually more often, as revealed in the Landers earthquake, the fault displacement is like the right pattern of partially distributed deformation. The total displacement accommodates overall the on-fault offset that is always measured in the field reconnaissance. The rest of deformation is distributed off the fault plane. This pattern is systematically observed in the Landers through an aerial detection techniques like the Cozy core. Okay, this is how I set up our dynamic rupture model. In the middle, light green curves are the pre-rupture mapping that is prepared for the Alquist per hour earthquake zoning, namely the prior information we know about future earthquakes. Red curves are the surface ruptures of the Landers. We see they are correlated spatially For better quantifying the future hazard in tractable manner, we simplify the geometry in this region as a three-segmented fault plane as the thick black line. Tectonic stress is derived and inferred from previous stress field model and the dynamic rupture modeling results. The applied stress in our model has three different orientations depending on the location as the blue arrow shows. On top of the three-segmented fault plane, we also add geometrical roughness, very small scale, to capture the modeling uncertainty and add a long strike variability. Thus, we can see the shear and normal stress are both per perturbed by the roughness. In terms of the rock materials, we adopt a 1D Mojave velocity model that's adopted from the SCAC BBP module, and also we apply the Hawk-Brown plasticity inelastic model to generate the all-fault inelastic deformation. We simulated two components of horizontal ground deformation. I placed it here and here. We follow the error measurements of fault displacement because it's required to stack fault parallel displacement within each window and obtain a similar partially distributed deformation pattern. The nomenclature in the study we used is denoted here in this figure, and the total displacement is a projection from the far field deformation, so from here to here. So the on-fault displacement is the offset on the fault strand. The fault zone width, denoted in the orange box, is a quantity measuring the spatial extent of a shear string. On the right side, we compare the simulated on-fault and total displacement with Lander's dataset. Especially, the simulated total displacement is overall increment with cumulative displacement in the observation dataset. We reproduce amplitude and the location of the peak fault displacement and roughly the statistical characteristics of the both on-fault and total displacement. Then we statistically compare simulation with data. This figure shows correlation of on-fault and total displacement in simulation and the data. Both show the similar tendency that the total displacement is systematically larger than the on-fault displacement, and the best fitting slope between the total and on-fault displacement are very similar. This is data, this is simulation, and this slope may help to quantify the unknown total displacement in some ancient earthquakes. OFD is all-fault deformation, difference between the total and on-fault displacement. OFD ratio is the ratio between the OFD and the total displacement, which implies how much displacement or deformation is accommodated in the all-fault regime. Both simulation and observation show OFD ratio to follow the normal distribution, and the mean value of OFD ratio are very close. 42% for simulation and 46% for observations. For the width is a little bit different. Simulation still follow the normal distribution, but the data follow exponential distribution. That is because our simulation is incapable to model the two small-scale fractures. It is a scale gap between simulation and reality. But the mean value for the width of simulation and observation is very similar. The 146 meters for simulation and 154 meters for observation. Our simulation also models ground motion even though it is a byproduct. We perform a sanity check for validating the physics important to ground motion is also properly modeled. Red curves here shows the mean bias of a dynamic model relative to data from 1 to 10 seconds. The gray shade here is the range of the 4 GMP median prediction. Relative to GMP, our dynamic model will address the event term of the unilateral rupture. In general, our dynamic model captures ground motion in the period from 1 to around 6 seconds. A longer period of misfit may be caused by the 3D velocity structures. To capture the modeling uncertainty, we relax some input parameters like tectonic stress and fault roughness. We create a suite of rupture models and use resultant magnitude to generate a bin average of the fault displacements. As similar showing in the earlier model, the location of the peak displacement is well consistent with that in layers. It implies that information of fault and stress orientation are important to a fault displacement. And here we make a magnitude match test. We pretend not to know the magnitude of lenders, giving our simulated templates compared with displacement, observed displacements, and a gradient. Which magnitude being average curve is your preference to match lenders? I will choose this curve and this curve, which corresponding to the magnitude 7.2 and 7.4, which just cover the ground truth of the magnitude of the letters. The scaling between the mean displacement and the magnitude is always used by the PSHA and the PAFDA models. Our own fault displacements are close to the previous empirical data and the scaling law. There are 4 new data points of Landers, Darfield, Hector-Mice, and Balochistan, showing the errorly derived displacements are systematically larger, and we simulate the total fault displacement or closer to the 4 datasets. Using the empirical dataset or on-fault displacement missing off-fault deformation may be under predict the fault displacement hazard, but the new observations are too few to support perfect model development. Therefore, a validated dynamic rupture model like the one we used in the letters has a potential opportunity to supplement the observations and reliably quantify the fault displacement hazard. Okay, take-home message. Dynamic rupture model is a viable approach to quantify the fault displacement hazard. The simulated fault displacement and relevant metrics are consistent with rows observed in Landers earthquake. And the ground motion is also consistent with the data. And more importantly, dynamic rupture is considered as an effective model serving for both hazard of fault displacement and ground shaking. Thank you very much.